Welcome everyone to another in-depth look of state-of-the-art and state-of-the-art vintage retro back then 30 years ago. Case in point, the upcoming Intel AMX instruction set. AMX for advanced matrix extension, of course. And as in previous videos, agreeing with Linus Torvald there was AVX2 and stuff, not that easily general purpose usable, and quite some logic gates wasted in the CPUs. What this allows here, this AMX, is accelerating, as the name implies, matrix operations, crypto, science, and so on. And not unlike we had this in the breaking news Centaur of all already 2 years ago, this rather impressive, but Centaur being Centaur, probably not getting to market in a couple of more years, and then it's already less impressive, because what they've done here, they have some AI coprocessor thing that I find much more, at least on the presentation slides, much more useful. So not only Intel, so also Centaur. As usual, a recurring theme, not only today for those who are new to this stuff, but especially back in the 90s, often not always the fastest, especially not with math coprocessors. And I wanted to, so this is just like, there are new AVX2 on steroids coming, of course, games and stuff will really use it, server process and so on. But in this topic I came about a truly hidden and rare and not well-known thing, the IIT of all companies. You probably never heard about this. This fine thing here, may I present to you the IIT 2, 3 and 4 x87 advanced, of course more advanced than Intel math coprocessor. What all those, I had this here already, previous video there a year ago. Cyrix fast math. Of course, back in the day, normal people like my father's PC and friends and family, nobody had a coprocessor in their 2, 3 or God forbid IBM XT 8086, 8088 times. I did not know anybody, not one person who had a coprocessor or a math coprocessor. Sometimes I run, when I was like 10 or 12, started some emulation, residential emulator thing there on DOS to emulate this mighty math stuff. Didn't really quite understand obviously what's going on there when I was 10 or 12. And this would be the matching thing, or matching, of course there were those from Intel, but they were not as fast, because this is of course fast math, because it's faster. And now, since I came along this one some weeks ago, of course I couldn't resist and found something on eBay. So what is the secret of this one? Of course, the Cyrix and IIT relatively similar, both faster than Intel, obviously, because Intel rarely were the fastest. But this one, what I didn't know until even I did not know until some weeks ago, this IIT, since 287, 3, 487, they have a secret, well, not so secret, it's in the data book, but hidden, oops, sorry, so much to having the wrong focus. Hotkeys, Wayland, so yeah. F4x4, you probably never heard about this, 4x4 matrix multiply instruction that allows computer aided and 3D software back in the 80s and 90s to run potentially more than twice as fast than Intel, and that certainly is quite a thing. So what have they done here? Quite interesting stuff for those who are new to this in-depth programming, programming the Intel, the x86 like math coprocessor is actually pretty annoying. Also, actually, fun fact, the x86 coprocessor thing never was particularly fast, because as you see here, it is of course on an external bus, so all of this stuff, quite some added overhead, So, and in general, they were not quite fast, many instructions. We will see in a second how many. It's a lot of like 50 and 50 clock cycles for square root, or even 57 and stuff. So, but certainly, additionally, the programming was relatively annoying. Probably most in the audience have never done this, especially those who are new to this and have only used SSE, AVX. So this is the block diagram of this math coprocessor stuff. And what is a little bit not unique, but different than normal general purpose programming, for sure, you will find other examples that use this kind of stack. So they have stack. So what could be no more annoying than real mode and segmented real mode and this complex instruction architecture? It's like, yeah, make this registers stack. Thank you very much. That means you can't really what normally on MIPS and Spark and ARM and modern x86 you can freely address those registers. You could not. You could pop and push to this stack there and only address them randomly for operations like add stack relative 6 to stack or stuff. Not particularly amazing to program and work with, and certainly performance as you would imagine from a stack-based register set. Also 8 registers only, as the usual illness that is super complex architecture, yet only very few registers. x86 general, but also the floating point. Only 8. So this makes working with this stack of 8 registers not particularly high performance. So what IIT has done is adding 3 banks of this. And why is, first I was wondering what the heck are they even doing there? And the design choice here is relatively simple. So they, for some, probably for their high performance computer science and CAD, computer aided design customers, they wanted high performance 4x4 matrix multiply, exactly what you need for a 3D world. My previous videos, Verge, Voodoo, Silicon Motion Links 3D, and some other low-level stuff. So if you have a 3D world, you have their vertexes, or not a game world, but a computer-aided design model world. You have 3 coordinate vertices x, y, z, and to transform these in a 3D space, you need a 4x4 matrix. And IIT, probably, I assume, by the way, IIT stands for Integrated Information Technology, of course, a little bit integrated information technology, something Inc. So the design choice is, okay, we want to accelerate 4x4 matrix multiply in the 80s, no less, right, with microcode here in their advanced math coprocessor. How do they do this? So they, obviously for a 4x4 matrix, you have 16 values in your 4x4 matrix, and you obviously cannot store them in your 8 shady Intel x87 floating point register. So it's like more, maybe they were arguing to make those just extenses. Not sure how exactly they came to that, but in the end they decided to make 3 banks of this. So this is IIT specific, AMD, Cyrix, and all the others don't have that. So IIT only 3 banks of this, making this a whopping 24 freaking floating, 80-bit even, right? In the 80s, 80 extended bit precision, 24, so that you have your 4x4 matrix in 16 of those registers, namely in bank 1 and 2. Of course, we start counting at 0, so bank 0 is a reset default bank of normal Intel and AMD Cyrix compatible stuff. Bank 1 and 2 for your additional stuff. Fun fact, you do not necessarily need to use this for 4x4 matrix multiply. You can freely use them, so you can just switch between the banks. That means you could potentially also accelerate other floating point code where you need more temporaries, more other previous values and constants and stuff, and you can switch between them. But fun fact, given that only IIT advanced math coprocessor supported this, there's only like literally 2 or 3 software using that, and now there is mine, so maybe Now there is 4 software supporting this, because I've of course written some fine assembly to test this, and I show you at the end how that looks. And yeah, so extending this, all the other stuff is fully compatible. Also, how much faster is this? So not only with epic thread-ripping AMD Ryzen, but also already in the 80s and 90s, especially floating point coprocessors. Many of the compatible clones were way faster. Also the Cyrix Fast, it's already in the name, right? Fast Math 1. Also, I think nearly twice as fast. So yeah, similar. I think similar to this, the IIT and the Cyrix, similar. IIT so super slow, right? If you ever had one of those Intel 83, 87, it's like, yeah, floating point addition, 23 cycles, IIT 12, multiply 28, yeah, 28 freaking clock cycles at 40 megahertz waiting for your floating point, 80-bit precision floating point, of which you only wanted 64. So yeah, for those who know that already, this excessive precision not really worth much and causing more bugs than good. And like, yeah, thank you very much. All we wanted is 64 or 32 or 64-bit precision, but Intel gave us a whopping 80 for, yeah, 28 clock cycles. Thank you very much. IIT 17, so basically everything as you see here, nearly 1.9, 1.6, 1.9, 2.5. Here this is a square root of like 119. It's like, how slow could stuff be in the 80s and 90s? Yes, 119 clock cycles, but thankfully IIT to the rescue, 2.5 times faster, only 48 clock cycles. Tangens and stuff, 384. And this additional instructions, so all of this stuff is compatible. And now let's take a look on the really interesting thing, 4x4 matrix multiply. So what they've done here is adding 4 custom opcodes, DB, E8, EB, EA, and F1. And the first 3 are merely used to switch the bank for your additional floating point registers. And the last one is one and only 4x4 matrix multiply. And also best here, we're pressing the right button. Here's some example stuff that reads a little bit. Yeah, do we not have, was he not? It's an OCR, not the best scan, and OCR documents. The search is not the very most amazing. Do we have here typical clock? Here's also typical clock count. So in case you were wondering, this, of course, what does it do? It replaces, and by the way, I'm pretty sure here was a nice nice formula somewhere. This is, of course, quite some multiplication. So internally, this is like 16 or so multiplications and at least 16 additions. Here, 4x4. So we have here 1, 2, 3. Okay, it's only 9 additions and, or is it? 9 additions and 1, 2, 3, 4. Yeah, 16 multiplications. I don't particularly like the wording here. They say designed to solve the following computational intensive problem. It's like, yeah, I wouldn't call this solving a problem. I would call this evaluating formula or something. But anyway, evaluating expression. So yeah, this is what this is doing. What Intel is doing now potentially in AMX, kind of sort of 30 years later. Here you have it in the 80s. And this data book leaves a little bit to be desired, because I naively, so they don't like, they only write here the coefficients A33 to 3 and so on are stored in bank 1, the other A31 and so on in bank 2, and of course they don't further specify the order. I intuitively like type something in, and of course I got this reversed so much to here. Data books, please specify this stuff a little bit more precisely. And X, Y, Z, and W, the input and output data in register bank 0. This setup, of course, allows, or you will see in the end, but what you would normally do in a 3D game on your 3 or 486 or CAD program is, of course, only load this world matrix once for your current model view, and don't modify bank 1 and bank 2. So the way this speeds stuff up more than 2 times so is, of course, if you would do this in Intel standard 80, 87 floating point math, you would need so many load so many values that you would constantly load and pop and load and store all your values from floating point memory, temporary registers, back and forth from memory. So this is how simply on-chip storing these 2 additional banks of floating point values makes this so much faster, even if it in the end takes 200 whatever something clock cycles. So this is how it's storing. They have some testing. Testing this, they only load here 1. So like, yeah, thank you very much for this example. It's like, yeah, loading only once helps me not very much for figuring out which place those go. Although they have here, is this here? Also, yeah, okay, they have here something, but yeah, they only load here a source index relative 10. Although maybe from this, okay, probably potentially from this, you probably could derive the order of this coefficients. Anyway, so yeah, really interesting. I always find this like hidden gems of vintage retro stuff that probably next to nobody ever heard about. And fun fact is this, unless someone at NASA or somewhere used it, I guess not much software, many people, I don't know if more than 100 or 1,000 people in the world ever use this, because who even freaking knew this instruction was in there, and then only like one or two CAD programs ever used it. So yeah, the chances that this instruction got ever used are like so zero, that close to zero. Anyway, let's see how this works in praxis. Of course, I took a proper 386 out for that. Here, one of those boards, previous video. For this good testing fun here, not the highest, just some random garbage, obviously. And tested that for you yesterday. And so that is the test program I came up with a regular GCC-based direct DOS.com executable stuff. Defining here this extra, of course, no assembler and compiler knows about this, so defining this here ourselves as db e8, eb, ea, and f1. And then simply using this in ASM volatile, also yes, some matrix 4x4 to be stored in bank 2 and 1, just a comment here, just the identity matrix. The 2 I only use later for testing, of course. Normally in an identity matrix you would have there a 1. I only use this for testing and scaling. So also previously I had here 1, 2, 3, 4 or something, but just for testing it's like just a tiny little bit differently to better check that this is 2, 4, 6, 10 in the vertex that we pass in there for transformation. So again, initially 1, 2, 3, 4, now 2, 4, 6, 10, just for a little bit better, because otherwise with 1, 2, 3, 4 and you get there like 1, 2, 2, 4 or something or similar stuff. I wanted just more unique values. This finit is floating point init, clear exceptions and stuff. They have this also. It's not entirely clear to me if they have this here in their example. Floating point init, fwait, and then bank select. The order here is for me a little bit strange because they have init. So init also probably resets the floating point stack pointer to the beginning, to the top. So for me it's not super entirely clear whether we really need this time wasting and clock cycle wasting fwait here. But yeah, for now I just mixed here some in. Also, this is a little bit, they switch bank, fwait, switch. Also although I think the top of, there you see this stupidity of Intel coming up with this glorious idea of having a stack-based register indexing thing here. I think this register top thing is only global ones here, so the banks are only the values, so probably it does completely not matter at all whether you first finit to reset the top pointer to load more values or first switch to the bank. I'm mostly curious whether we really need f-weight there. But yeah. Anyway, for now I have actually I do without f-weight, just looking at this. Probably yesterday I thought, yeah, rubbish f-weight. Anyway, so what we do here is matrix vertex f-init floating point switch bank 2, loading the first half unintuitively in bank 2. I think their example does it the other way around. Yeah, they as you see, they again, doesn't matter if you whether you do this first or that. So this is just to have this more aligned and or loading this, but again, probably performance impact next to 0. Loading the first half of the 4x4 16 values of the matrix in the IIT specific bank 2, then f-init reset floating point stack pointer also, including other things, switch to bank 1, load all the stuff in there. Of course, so this is those values A in the matrix 0, 0, 1, 2, 3, they're indexed in the matrix. I hand computed those here relative to the programmer specified memory reference passed in there, so plus 0, 1632. I might use GCC assembler template a tiny little bit out of spec. Leave in the comments below if this triggers you. So loading the second half of the matrix from 0 to 3, 3. And then last but not least, loading the vector. The vector, of course, only filling half of those floating point registers. That, fun fact, if you were going to write state-of-the-art high-performance computer-aided design software in 2021 for those processors, you still have 4 more precious floating point registers for other temporaries or other calculations, and can still always leave your worldview coefficients there of the matrix in those additional banks. Then here's a mighty instruction only supported by this advanced math floating point coprocessor, F4x4, f-weight. Probably I should actually check whether this is really necessary. But and then, so this loads this floating point load short, meaning 32-bit. Their example, first of all, this is Intel notation, this is AT&T notation, and this needs explicit, what was it even, ZFLD, or what was the other? Anyway, I'm loading here for memory efficiency just 32-bit floats, not 64-bit double floats, and storing them again. So loading this vector, storing this vector, GCC assembler template, outputs. Also, yeah, this triggers me each time. Why are the outputs first? And I personally, if I would have designed this bloody assembler templates, I would have started with the inputs and then the outputs. But somehow, yeah, probably each person ever doing that always mixes this. And anyway, outputs first, then inputs the matrix as memory, output the vertex there, and clobbers the floating point stack just in case that matters. And then so printing, multiplying this, printing this. I think did I leave it in? Yeah, this is still in. I could show you a screenshot, but of course we can also, by the way, this probably, yeah, this doesn't have a CMOS battery, so much too. I could have done that before the video, but here we are, F1, oh wait a second, F1 to resume is not good. Oh, okay, F1 to resume was good. Amazing BIOS goodness, right, for all of those who are new to this stuff and only know the graphical BIOSes of nowadays. Oh, wait a second, I think this had an advanced also the Pro was there some, or whatever, doesn't really matter much. Here, autoconfig a little bit faster, I think that worked, and auto detect hard drive, I think that also even worked. Amazingly, right to CMOS, and boot our example. And of course, only scientific curiosity, unless you wanted to write high performance DOS CAD keyboard error. Not sure, I saw that there on the board previous video, so not really sure if we still get a keyboard error or if it's some incompatibility with this USB based thing, but whatever the case might be, FX4X. And 24620, a little bit the first time it didn't work. Obviously I had a couple of guru meditations and resets and stuff with this nature of low level software here. And then even when it was working, the order of the matrices was first wrong. So first I got there some other random stuff until I tried an error and figured out and cross-references more of this text. But yeah, there you have it. Really works. Maybe I someday write some more 3D thing just for the fun of it. And last but not least, one fun fact. This means also, because very few software has support for this stuff, that if you run this in a, it's also partially dangerous, if you run this in a multiprocessing environment like Windows or Linux, and you use those banks, right? You know operating system. I checked the Linux kernel, obviously it didn't see support for that in there. But yeah, fun fact, a little bit dangerous, this custom stuff, because if the only thing you need to do is run this FSB 1 or 2 and switch the floating point state. Oh, wait a second. The kernel should still save that. So actually, okay, it's a little bit safer than I thought, because the Linux kernel, of course, refills the state of the other program. But if two programs run with this, they clobber each other the additional floating point registers, because the Linux kernel or any other operating system, Windows and stuff, only doesn't know about this, didn't implement saving this additional banks. So concurrent programs, if you'd ever run more like one high performance computer aided design thing, they would each other clobber this additional register bank stuff in whatever coincidence of nanosecond the task is switched and whatever additional bank was selected. So yeah, unfortunately you probably couldn't even optimize that if you wanted, because you need to store 3 times the floating point state, similar to MMX and SSE, which also need to store more of those additional registers, or AVX or AVX2 or AVX 512. And yeah, you need to do this safely to support this in some operating system. 3 times the floating point state, of course, nearly 3 times, or is it 3 times? Yeah, 3 times floating point state, save and restore. And you couldn't even optimize this, right? Because this additional instruction doesn't trigger any special exception that you could trap on. So you could not even determine when like from the kernel perspective, whether a user space program is running this exotic and rare instruction to optimize whether to only save one or all of those banks. But actually this leaves me to, you know what, this is even crazy just that I think about this. I think you can't even, correct me if I'm wrong, and if you worked at IIT, fun fact, I googled them, I didn't find much of them, no idea what happened with them, if they just got bankrupt or brought out by someone. But I think, now that I think about this, more so much to guru meditation and designing a safe kernel, because there is no state that you can determine which bank is currently active. I think you can't even make this to work for more than one application using these banks at a time in a task switching multiprocess kernel thing, because you can't restore the same bank that was active. That is actually interesting fun fact. Yeah, anyway, that's it for this video. I found this really curious. This is Intel, last but not least, this is Intel stuff, coming back to state of the art. The Intel AMX Advanced Matrix extension, I think it will not be used much. This is probably, so this is of course much more flexible than this one little tiny instruction from the 80s, much more flexible to configure a much larger matrix state of kilobytes, not like 8 but or 16, not 16 but 1000 or so. Whereas even the state set of also new. What else do we need more in complex instruction set architecture? That is Intel x86, of course, more new registers, 8 new tile registers, TMM0 to 7, maximum size of 16 rows by 64 bytes, 1K. So yeah, there you have it, 1K apparently. Personally, for me, last but not least, concluding this fun little ride here, for me this is not much, has not much value. I would much rather prefer, I said this before, similar to the AVX512 and stuff, I would much rather see a more general purpose programmable thing that are GPUs or was the PS3 based cell architecture of having this kind of high performance local memory of 1K, or the cell of course had more, I think maybe even 256, so much to Intel AMX in 2021's like, yeah, you get 1K. IBM, Sony and Toshiba and stuff in the 2000s, hold my beer, we give you I think 256. So much to the cell design being ahead of its time, because this is not that flexible usable, right? So you can only use this for one very specific task, and in my opinion it would be much more valuable to have a high performance general purpose programmable accelerator thing. Of course we have GPUs, and I would also argue Intel or this x86 in general, they freaking need to stop adding crazy stuff nobody will use, because similar to AVX512, you can't just use it, you need to specially program it, and you probably, the compiler cannot even, unless you have some specific matrix library for that, matrix kernel math, not easy for the compiler to just use. And even then, previous videos, you need to pre-compile this, and old software will not simply use it, and even new software will take years to support this, if even optionally they support this ever, simply because only the latest and greatest CPUs have it, and customers usually 99% of the time run yesteryears or the year before yesteryear's silicon. And so yeah, anyway, hope you learned something and enjoyed this. The sources are in my DOS stuff here. I think I in the meantime renamed this kernel just for the fun of it. If you want to play with this F4X4, here you have it. I think this should already be fully committed. Yeah, this is fully there. If you'd have some IIT 3 or 4 C87, I think I have the 4, yeah, I have the 4 C87 DLC. Fun little side project thing here. And I hope you learned something and like that, and to see you soon for the next videos and live streams to come.